Okay, this is kind of an intimidating point to be presenting. First of all, following up from like literal legends in the industry, people who are totally groundbreaking and tracking the path of where we're going to go in the future. And I'm kind of talking about technology and approaches that are like 60 years old. But I'm an old guy and I like old math, and that's just kind of the way it's got to be. So, but my topic today is actually really, really closely related to what Yuri was talking about. He provides the actualization, and this is sort of the direction of how we can get there. So, anyway, my name is Tom Howe. I'm a principal product architect for Hydrolix. This will be like basically the only even remotely sales pitchy part of the entire talk. But Hydrolix is a high performance data plane that focuses particularly on things such as telemetry and log information, streaming it in, storing it for long periods of time, and making it accessible very quickly. So as we're thinking about how to steer our traffic, that becomes a big part of the concern, is making sure that you have a sufficient data plane. So let's hop right in. The first piece that I wanted to think about is when we talk about traffic split, when we talk about having multiple CDNs and wanting to distribute our traffic across our CDNs in the most efficient way, we think often about like, okay, well, we want 15% here and we want 25% there and 60% there, and we can't exceed our capacities and all that, which is absolutely right. But it's important to remember that the optimal split is just a target. It doesn't necessarily tell us how to get there, and it is bounded by lots of different constraints, including time constraints, including business constraints. And what we need to really be focusing on is not just what our optimal distribution is, but we also need to be thinking about how do we get there and what are the steps that are required for us to get there safely and within our own set of business constraints. So I'm going to do two call-outs right now because there were talks at this conference which are already set the groundwork. So Yuri, obviously, none of this works without none of it works effectively without HLS content steering and Dash content steering, as well as the work that he's done in the past around using constraint problems and constraint solving at the edge in order to make ideal distribution. So thank you, Yuri. And Bradley yesterday, literally none of this works without consistent, trustworthy, and reliable data about what's going on in your state. So if you aren't collecting data through OTel mechanisms or others, I strongly recommend it because it unlocks all of these things. So math. The goal of this problem is actually a fairly simple one. It's to say, how do we get to our ideal distribution over a time period and not risk overshooting? I'm not really talking about AI here. And like I said, I'm talking about 60-year-old math. But this all depends on having AI models that can actually drive your predictions. We need to know how to get, we know where we want to get to, we know where we are right now. But the idea is that over time, that may change, and how we get our path to there is different. So what I've written up here is basically a relatively simple constraint problem that is very similar to kind of the myopic views that have been used in the past, where we're looking at how much traffic we have right now and we're going to distribute it according to that process. The big change in this is, instead of just looking at the one planning horizon and saying, okay, we're basing this on the amount of traffic we see now, we're doing a look ahead. That doesn't sound very creative or anything, and it's not. But that look ahead allows us to use a receding horizon to decide where we're going to move traffic next. And again, with the ML, the AI, determining what that look ahead plan looks like is critical to use the emerging technologies that we have. Once we have that information of here's how much traffic we think at time t to time t plus 4, we can then apply a pretty straightforward constraint solving problem where we find the peak of the traffic over that time period, bounded by our constraints. So in our case right here, I'm just using a very simple constraint, which is we can't change traffic to any endpoint more than 10% per time step. Now, there's a lot of reasons why you would do that, not wanting to overshoot. In fact, when I've done this in the past with the more myopic view, we used a pretty simple control mechanism that didn't account for future, but would allow us to smooth things out. So the idea is we take the peak of the traffic over the next 5 steps, and then you apply a classic linear optimization model to find the path to that peak between where we are and right now. So in this case, let's say, if the peak is going to be at T2, we try to find the optimal path that optimizes based on our cost. We're looking to minimize our congestion. We're looking to minimize our price that we're spending, and then find the path that aligns to the constraints and will get us from where we are today to that optimal point. Now, here's the critical thing here. We don't actually care about that peak time at this point. All we care about is how do we get there and looking at that first step. So we do the whole optimization and then essentially throw away everything except for that very first time step and apply that. And I'll show you kind of what this looks like. So if we assume that we have this forecast demand ramp right here. Everybody talks about the World Cup, so let's assume that this is the World Cup. I don't know. I mean, the France and England game was very exciting, so let's say that maybe this is France versus England. We have a point at T5 where we've hit our peak traffic already, and so it's important to kind of keep this in mind, given that we want to shift traffic from between CDNs in order to reduce congestion. The second thing I want to call out is that this is making an assumption that we have one CDN or multiple CDNs that have a distinct lower cost, but also a specific congestion limit. When I was at Disney, we had our own in-house CDN, which was ridiculously cheap to run, but the constraints on capacity were extremely tight. So this shows what happens when you have used that myopic view to predict traffic and to route your traffic over time versus that optimization from point A to whatever the peak is. And what you see is at the very beginning, everything is fine. And when the myopic perspective looks at the amount of traffic that's available, it's totally reasonable for it to send all of it to that cheap CDN. Unfortunately, though, because the traffic has increased so highly, it very quickly enters into this area where we're running into a dangerous amount of traffic and over congesting our lines. The look ahead sees that at time T5, we're going to be hitting a max. And so then optimizes a plan to get from where we are today to a safe amount of traffic in T5, but bound by the constraints of only being able to reduce traffic 10% each time. So this is a ridiculously simple example, obviously, because the math works out perfectly. 4 steps will get us to there, And so it's not necessarily realistic of the complexity that you see in the real world, but the ideas still hold, and this is, illustrative for that purpose. Okay, so there are 3 layers to how this works, and they reflect directly to what we've been talking about and what we've seen throughout the course of the week. Or 2 days, I guess. Wow, it feels like a week. Yesterday was dense. The first piece requires accurate telemetry. You have to have data about what is coming in, what the state of your system is at any given point in time. Prediction, agent-based prediction, ML-based prediction is worthless if your data is worthless. I guess that's the old garbage in, garbage out analogy. The second piece is the optimize, and that's where we can leverage some of these controller programs that we've been talking about, the linear constraint-based programming. It's designed to take hard problems and hard constraints and do them very efficiently. When we're thinking about content steering in particular, a lot of the compute realistically is going to need to be done at the edge in order to make the reactions very quick so that you see and you observe congestion problems and you have to make the decision at the edge. You can't run a full agent model or a full neural net at every single edge and have it be functional. So by reducing it down to a linear constraint problem, we can run that optimization at the edge. And then the last piece is the control loop. We don't want to be just focusing on what we're seeing right now. We need to be looking at where we're going to and how we're going to get there safely. What we can see is that on the left, we see sort of the myopic approach where the traffic is going up. We see the cheap CDN share. As the traffic goes up, the cheap CDN share very quickly exceeds its maximum congestion. which is the fundamental problem that we're trying to address. Whereas on the right, when we're doing that look ahead and each step calculating what do we need to do to get between where we are now and the peak, we're able to keep it right in that sweet spot at the top, right at the realistic limit of our traffic share. So the right side is better at accounting for the cheap CDN cost within the constraints of what we're trying to accomplish and what is put onto our load. Now, this is fully acknowledged that this is simplistic. It's missing a whole lot. It makes an assumption that you're looking at convex constraints and things like that. So there are big things that we should do. But the key part is to make sure that we keep that cheap, fast work at the edge being done in a highly optimized constraint problem solve. So other things we would want to do, though, like are 2 timescale optimization. Right now, we're doing just optimization second by second, essentially, to look forward and make sure that we're keeping ourselves safe. But that ignores a lot of like stepwise constraints that you might see. There's certain cost models for CDNs where, if you get up to your limit, you prepay, you get up to your limit, and if you exceed by 5% for a certain amount of time, then you get a huge penalty. That can't be modeled in what we just showed. But with a 2 timescale optimization, you can have one path that's focused on that, those longer term optimization components. The other thing is like we're using congestion as a strict proxy for quality and quality of experience. That's not really realistic. But when you have CMCD that provides buffer sizes and overruns and things like that, you can start to do a lot more in terms of the optimization. And then, the model is great. The prediction model is great, but everything you do is only as strong as the quality of that model. So if you want to do longer time horizons for forecasting, that's great, but you have to account for that uncertainty in the decisions that you make every moment. And realistically, this doesn't. This assumes that you have perfect knowledge of the future. Well, we don't, but maybe someday. Okay, so this is basically the control loop that we're looking at. And I'm not going to go too far into it because it's actually not that complicated. And I'm actually starting to run out of time. But the idea is that the control loop is from getting the telemetry and accessing the telemetry, maybe through a high-performance product like Hydrolix, I don't know, reading through it, aggregating, getting that information to the edge, doing your receding horizon optimization, and then repeating the process, using the actuator of content steering to move on to the next step, and then repeating the process for the next time spot. So when you want to think about rolling this out, I want to be clear that each one of these steps has to come before the other. So replay, telemetry, you've got to have telemetry before you can do anything else, and you have to have reliable telemetry. You have to be able to shadow it. You have to have live inputs where you can model these things and not immediately try them out. That's a no-brainer, right? Advisory, you want to be tuning your model constantly. Operators need to be reviewing the decisions that are being made in the shadow. Guarded, this is basically software rollout 101, right? You want to make sure that at each step you have confidence in the step. And then the important piece is the controlled measured experiment. You want to have a continuous flow and feedback loop to make sure that you're tuning things correctly. So the idea is we want to be able to do high performance, effective routing at the edge, and we want to have it be safe. What I've tried to propose here is a pretty simplistic approach of how you can get there.